So just to do a bit of a recap, we studied 4 different kinds of stochastic processes that can exist, right? So we can either have a state space which is discrete or continuous, and same goes for the time domain as well. And the chapter that we are going to study today is titled Markov chain. And you can clearly see that we are going to have a look at the state space, which is discrete, as well as the time that is discrete. So that is the scenario that we have. And we looked at a very nice example of a Markov chain, which was this model, no claims discount model. So this is the kind of model that insurance companies might use if they want to deter the claims. So what happens is, we know that if there is a certain claim incurred, let's say if you start at 0%, then you will again still be at the 0% discount level if you incur a claim in that particular year. And if you do not, then you move on and you move up to 25% discount level. So you won't have to pay that much of the premium, and you will have basically 25% off of the premium. So that's the case. And this is just one particular example of a Markov chain, where you are looking at the discount levels. But again, there are so many examples, and we will have a look at those examples. And the thing that we want to remember from this particular model is that we are looking at state spaces, right? So all the things, so these are the things that matter a lot, right? What discount level I as a policyholder am on in this particular time. So that defines your state space, and you denote it by 0, 25, and 40 here. But again, you can also change these state space notations. So let's say you can write it here, 1, 2, 3. So you will have state space 1, 2, and 3. 1 will denote the 0%, 2 will denote 25%, and 3 will denote 40%. So that's not a big deal over there, but the time domain will have to remain same. When I'm talking about 0, 1, 2, it's still, it has to make sense. You can't just, assign ad hoc numbers to this time domain. So again, in all of the questions that we will be studying about this Markov chain models, the main thing, the art here is to figure out the state variable. Not every time you will know what state variable will there be. So sometimes you are only given a particular scenario, and you are the one who will have to devise a model. So time step would be fine. You can take discrete or continuous depending on, again, what kind of questions they are asking you. But again, state space is something which is kind of critical, and it is really not something which is mechanical, that you have to do this and basically this will be the state space always. That need not be the case. So again, we'll see at how we can define state spaces. But again, what do we know about state spaces? We know that, so again, whenever I'm talking about a Markov chain, what did we study? We also studied something about this, right? The Markov property. Can someone summarize the Markov property for me in a line or so? Do you guys remember? What does my Markov property say?
That the probability of some element, it doesn't depend on all the past values, it depends on the present.
Yeah, so kind of, I get what you mean to say, but again, just to be, much more precisely, what it says is that if I know the current state, basically, if I know what has happened today, to predict what's going to happen tomorrow, I do not need to know beyond today's information, right? Basically, all the past values do not matter much. And what matters is only the current state to predict the future state. So that's it, what this is trying to say. So basically, to see what's going to happen at xt, you only need to know xs. Not, I have written this equal to, right? Yeah. So yeah, we only care about xs, and all of these do not really matter much. So I guess that's it. And now we'll study about the Markov chain in details. So yeah. Again, remember any stochastic process that we define, what matters is the state space, the time domain. And here we will be looking at discrete time domain and discrete state space. But again, if I say that I'm looking at a discrete state space, what I know is I can either have, so let's say if I'm looking at the NCD model, I have state space like 0%, 25% and 40%, right? But again, can you guys imagine a scenario where I can have infinite number of these state spaces? So here I have 3 state spaces, right? Which is finite. And I can count this. So this is basically countable and finite, right? But again, can you guys imagine, or what do you guys think, if it is possible for me to define state space infinitely? Do you think it could be possible? Anyone? Okay, so maybe as of now, we don't know how to answer that question, but we'll have a look at that particular question as well. But now to simplify the analysis, let us assume that we are looking at finite state space, which is discrete, and we are looking at the discrete time domain as well. Okay, and let us look at this NCD model, and let's continue with what we studied earlier. Let me just check if we studied down. Okay. So when we studied this particular model previously, what we said was we were looking at transitions, right? And these circles denote and these arrows denote the transition. So basically this P here denotes the probability that I will move, let's say, from 0% to 25% in the next time period. So this is just basically one step transition probability. Let me just write all of this again. Yeah. So what we are going to observe is someone can move from 0 to 25%. Yes. And then they can also move from 25% to 40%. They can also move down if, let's say, there is a claim incurred, and they can stay at the same level as well. So again, let me just erase this. And these people can basically stay at the same level as well. Can someone go from 40% to 0% in one time period? No, right? So what I'm assuming is that this P denotes the probability that there will be no claim, such that 1 minus is the probability that there will be a claim. So again, if you're moving down, it means there was a claim. This means there was no claim. And again, if you don't move down and if you stay right there, it means there again was no claim. But again, now, if we want to show this transitions, the one thing that you can do is to draw these diagrams. And the other thing you can do is to work out the probabilities in a much more intuitive manner. You can also create a transition matrix. So I call this a transition matrix. So what I'm doing is I'll be creating a matrix with, let's say, 0, 25, and 40%. Okay, and here I'll have 0%, 25%, and 40%. So I have one particular matrix. So remember the example of credit ratings that I discussed in the previous lecture. We used to have double A, triple A, let's say, and B and so on here. So we would be looking at, let's say for this example now, MCD, what you want to look at is what is the probability that if you start at 0% today, you will end up at 0% the next year as well. And that you will write here. And again, the similar thing will go for here. So let's say if you start at 25%, what is the chance that you will go to 0% in next time period? So you will write that particular probability here. So now can you guys help me to fill up these blanks here from what you observe in this diagram? So what do you think I should write here?
1 minus P.
1 minus P. Okay. So maybe now I can say that, my P is 0.75. So there is a 3/4 chance that there will be no claim. So it will be 1 minus P, which is just 0.25, right? And from 0% to 25% will be this particular arrow, right? Which is just 0.75. And then from 0% to 40%, there is no arrow. And there's no possible way that it can move from 0% directly to 40% in the next time step. So it's going to be 0. So again, one thing that you observe is that, we define arrows only for the transition probabilities which are greater than 0. We do not sit and just, denote these arrows for all the possibilities. We only take into consideration the accounts where this is not 0. Okay, and then what should I write here? From 25% to 0%?
0.25.
0.25, exactly, right? And here what I will have? There's no way it can stay there, right? And this will just be 0.75. And again, if I do the same thing, there's no way you can go from 40 to 0, but you can go from 40 to 25 if you incur a claim, which can happen 0.25 times. And here you will have 0.75. So again, these numbers that I have written in decimals denote transition probability. So let me just write it here, that these are actually transition probabilities. So again, these terms might seem a bit fancy, but again, it makes intuitive sense, right? What is the probability that you will transition from, let's say, 0% to 25% is denoted by this particular cell here. And again, now whenever I'm saying that I'm looking at a transition matrix, what I do is, I don't care about these lines and everything. What I will be doing is, I will just create a matrix and I'll, let's say, just, call my matrix P to denote that, this is my transition matrix. And just the usual way I write a matrix, right? So I will just write these, and you won't be writing it, in boxes and these terms, but you do know how each one of these rows and columns come into being. Right? So this is how your transition matrix will actually look like. So this denotes from 0% to 0, 25 to 25 will be this, and again so on and so forth. So again, these numbers also denote the transition probabilities. And now we know that, let's say if I have this particular matrix P to denote this one particular cell. So these are just notational things. So to denote this one particular cell, I will use, so again, you need to remember two things. One is that I comes before J whenever you write alphabets, and you think of row first. So we are going to denote rows by I and columns by J. Okay. So now to write this particular cell, what I can rewrite this as is, it is an element of the matrix which I denote as capital P here. But what element, right? This matrix has 9 elements. So I need to specify the row number and the column number as well. So my row is 1 and my column is also 1. So this right here denotes P11. So my P11's value is 0.25. And now can someone tell me How can I denote this as? What should be my I and what should be my J for this guy here? Anyone?
P13.
I cannot hear you well, Savi.
P13.
P13, right? Because we are looking at first row and we are looking at first, second, third column. So this 0 right here will have P13. So in theory, if you are going to, write these, you can denote that this is my P11, this is my P13, and similarly, just to give you another example, this will be P row third, second column. So this is my P32. So now, what does P11 represent? Can you tell me? In words, what does P11 represent here?
Transition probability from 0% to 0%. From
Right.
0 to 0.
Exactly. So to make things a bit easier, what we can say is, let me denote my this state as 1, this state as 2, and this state as 3. So now my P11 will denote what? Transition from state 1 to state 1, right? This will denote transition from state 3 to state 2. This will denote transition from state 1 to state 3. So if we kind of, ignore the fact that we're looking at 0%, 25%, 40%, and we just assign them random numbers like 1, 2, and 3, which are in tandem with the matrix notation that we've used here, it's easier for us to interpret this P11 here, right? We won't have to remember that my first row here corresponds to the 0% discount level. I can just redefine my state spaces as 1, 2, and 3. I know that, I'll have this in my label box that my 1 represents 0%, 2 represents so and so, and 3 represents so and so, right? So this P11 will become much more intuitive now. What this P11 says is that the probability that I transition from 1 to 1, right? My state 1 to state 1 in one step. So this is a transition matrix, and these are transition probabilities for one time step. So this could help you answer that, let's say if today I'm at 25% discount level, what is the chance that I will be at 40% discount level in the next time period? So this transition matrix will help me answer that. But again, sometimes you don't only care about what's going to happen in next time period. You also care about what's going to happen in, let's say, after 10 years. Let's say what's going to happen in the long run. So then what will you do? And those are the kind of questions that we will now see and we'll now learn how to answer. So again, if you observe really nice cool thing about this transition matrix is that each of these rows sum up to 1. Can someone tell me why do you think each of these rows should sum up to 1?
Because these are the probabilities.
Yeah, I agree. So these are the probabilities, yes. But then why don't columns sum up to 1? These are also probabilities, right? Why does only row sum up to 1, not columns? Think of what does one particular row represents.
Ma'am, because from 0% there will only be 3 possibilities. So the probability of all 3 possibilities should sum up to 1 for that particular.
Exactly right. Yeah, that is precisely the reason. So again, we see that if you are at 0%, let's say today, there is no way you could go elsewhere than these 3 possible state spaces. You could either remain at 0, you could go to 25, or you could go to 40, right? So all of these should ideally sum up to 1 because we're looking at probabilities. So it should either go here, it should either remain, it should go here, or it should go there. So addition of all of this should always be 1. So this is something that we might use later on to figure out certain things. I mean, let's say if you're given this and this, and you have to figure out this, so it's just easier, right? 1 minus the sum of these two. So you can easily do those to figure out the spaces that you might have in transition matrix, given that you don't have 2 blank spaces in one row. All right. So this was something about, the way we denote these transition probabilities. But again, what is what exactly is a transition probability? I think it might be a bit counterintuitive, but try to see this transition probability as a conditional probability. So what does this transition probability say? Given that I am at 0% today, what is the chance that I will be at 0% tomorrow, right? So I've given the current state, and that is why this is, you can think of the transition probabilities as conditional probability, and this will be in a way used to kind of prove something which we don't necessarily have to get into, and it's not really compulsory for us to get into the proof. But again, if anyone is interested, you can always, contact me to know more about how to prove this. So basically, we'll be studying particular equations that will help us derive not only the one-step probabilities, but also beyond just one-step probabilities. So now if I tell you guys, okay, so this was only half of the notation, okay? What I'm representing here, this P represents my transition matrix, right? And these represents my states. And I know what matters also is the time, right? What time I am currently in and how much forward in time I care about. So that you will denote, so let me just write it here. What you will denote sometimes is something like this. So let's say P11. What is the chance that you are at state 1? Basically, you start at state 1 and you end up at state 1. And let's say you are at state 1 in time period M, and you want to go to another state in time period N. So this is how you will be denoting. So this this superscript will represent time, and this subscript represents state. So in general, what you can see is that this is my I and this is my J. So you can, so this particular element, so this is one element from one transition matrix. So now I'm assuming that my N minus M is just 1. Okay, there is only one step difference, and then only I can use this particular matrix to figure out a value for this guy, right? So what I'm trying to say using this particular notation is that what is my probability that I start in state I in time M and I end up in state J at time N. And these M and N could be any numbers basically, but N should be higher than M, of course, because you're moving forward in time. And as of now, but again, so this is just some notation that you should try to take into consideration. And again, okay, so whenever I'm writing this notation M comma N, what you could also do is you can ask me a question that, why do I have to specifically mention when I'm starting and when I'm ending? I think, sometimes what might be useful is, this could be a bit of more information, so a bit of more cost. So sometimes what you only need is the time difference. So sometimes you could just denote this as, let's say Pij, and in bracket, if you just have 1 here, this will denote the lag. Not exactly lag. Shouldn't write lag. So this will basically denote the difference in time, okay? Basically, N minus M is just 1 here. So let us say that this P remains same for each T. So assuming that let's say you start at time 1, the probability that you will end up in particular states in time 2 are denoted by this transition matrix. And again, let's say if you are at time 2, the probabilities that you will end up in time 3 in respective states are again denoted by this, and so on and so forth for each of the time periods. Then we say these kind of processes are time homogeneous, where the time really doesn't matter. What matters is how much of far in time you're looking at. So it doesn't matter if you start at 2 and you end at 3. What matters is that there is a difference of 1. So the probabilities of, let's say, so the probability of 1, 1 when you're moving from 2 to 3 will be equal to the probability of 1, 1 when you're moving from 3 to 4 in time homogeneous case. And those are the cases where you will tend to just, care about this lag. So what you write is the difference, this one here. But again, if that is not the case, you will have to write this M and N to say that, here I was starting at 2 and now I'm starting at 3. So these need not be equal always. So again, these cases would be inhomogeneous, as we have already discussed before. So is there any doubt in this particular slide? I mean, is there anything which is even a bit unclear to any one of you guys?
No, ma'am.
Okay. So see, the thing is, the more better understanding, I mean, the clearer understanding you have of everything that we're doing sequentially, the better it is going to be for you guys to understand this concept. Because again, like in the previous chapters that we studied, this is, I mean, these chapters are all connected and interlinked. I can't possibly teach you one chapter before the other chapter. So even you can't understand one particular chapter if you haven't understood something which let's say I taught in the previous chapter. So I would highly encourage for you all to, be thorough with the chapters that we are trying to cover. Okay. So again, now we will try to study. So let us say, okay, maybe what I can do is, let me just draw a diagram first. So on my x-axis, I'm denoting my time. And let's say on my y-axis, I denote space. Okay. So my time, let's say I go from M to N. And my state space is, let's say, I to J. So what I want to care, I mean, the probability that I care now is this. So I go from time M to N, and I want to see what is the chance that I will go from state I in time M to state J in time N. And this is basically in probability terms. Remember, this is conditional distribution. So what I'm saying is that my xn, so this n corresponds to the t that you have. So my xn will be j such that my xm was I. Okay. So now what I'm seeing is basically if I have plotted this in graph, I start somewhere here and I end up somewhere here. So what is the probability that I'll start here and I'll end there? So I know that there are so many, so let's say I can go to that particular place like that, or I can also move in like this, or I can also move in something like that, or again, I mean, it basically could be any possible path that will make me reach my end goal, given that I'm starting from my initial point. So again, now how do you write this probability? How do you take all of these paths into account? So what you do is, again, remember, this M, N, I, and J are fixed by nature. These are given to us. So now what I will be doing is, I will fix a time, let's say L, which lies in between M and N. So my L lies in between M and N. And what I will do is, I will check what happens at this L. So let us say I have these. And what I want to check is, what happens at this particular L. So let's say if I join this as well. And let me just note that, the state space at this particular L for this particular sample path, I'm denoting this by, let's say, K. So this is what I'm going to do here. And now you know that this K is not fixed, right? Because again, if I take this sample path, okay, so yeah, I mean, this is kind of wrong. You cannot have the same sample path intersecting this thing twice. So let me just do a bit of a correction there, maybe something like that. Yeah. So basically it should be a one-to-one function. If you take a vertical line, you shouldn't get two y-axes over there. Yeah. So now that we have corrected this, what I'm trying to say is, I take any time L in between M and N, and I try to figure out for all these possible paths, what state space it takes at this particular L. So let me denote that state space by K. But again, for now, I have taken this sample path, so I get my K here. But let's say if I take this sample path, I'll get my K somewhere here. If I take this sample path, I'll get my K somewhere here. So again, these can vary. So now what you want to do is, am I audible? I guess, yeah. Okay. So what I'm trying to do is I want to figure out this probability, right? So intuitively, what will come to my mind first of all is that it should just be the addition of all of these things. The probability that, this will happen, this will happen, this will happen. So in a way, what you will try to now do is you will try to check. So now this diagram itself, I'm going to represent on, let's say, a 2D line. So let me draw a line here and M, N, L. And my state is I, my state is J. And here I say that my state is K. Okay. So again, this represents state and this represents time. Okay. So now what you have to do is you have to check how do you move from M to N. You can't directly move from M to N, right? You have to pass through certain stages in between. So what are those stages? If you take all of those stages into account, all the possibilities of what state space can there be, then you would essentially be adding up all of the probabilities, right? That will lead you from M to N. So what you will do is, let me just denote this. So let's say if I want to denote the chance that I hop from I to K in time M to L, I will denote it as Pi to K M to L, right? And to denote a move from L to N, from K to J in time L to N, I can write this as Kj L comma N, right? So now if I have to figure out my probability that I move from M to N, what can I rewrite this as in terms of this guy and that guy? Can anyone say?
Probability I to J M, M comma N.
Yeah, that is what we have started off with, right? So M to N, I to J, that is good. But now what I want to do is, I want to split this in two. And what I will denote is, one is the probability that I move from M to L, and second is the probability that I move from L to N. Sorry, from I to K and then from K to J. So what you do is, that, what's going to happen is, this represents a transition probability. This represents another transition probability. So the probability that I go from state I to state J in time M to N via this particular K here. So what I'm trying to say is that when I move from I to J, I pass this particular stage. So you can see this clearly here, right? If at all you want to go from I to J, there will be some intersection on this L vertical line that you will get, and that intersection will be your K state space on the y-axis. So you know that in one way or the other, if you're going to go from I to J, you will have to pass this K route. So the probability that you will go from I to J can also be summarized as the probability of I to K multiplied by the probability that K to J. So what I'm going to do is, I'm just going to rewrite this as Pik M comma L Pkj L comma N. But again, now we know that this K and this L was arbitrarily chosen by us. So what we want to take into account is all the possible keys, right, for all different sample paths that we can have. So I'm summing up this thing for all the keys. And this, so again, this is, this should be small p ideally. I hope it looks like a small p. So yeah, this is what you will have. Let me just Does this make some sense to you guys? Or no? So basically what I'm trying to do is, if I want to go from I to J, I know I will be passing through K somehow. But again, what I want to do is, I'm summing it up across all the possible values of K. And when I do that, I'm essentially summing up, I'm taking into account all the possible sample paths that will allow me to move from this to that. And that is your probability here, right? So again, I'm trying to check the probability that I will go from this to this times the probability that I go from this to that. Then probability that I go from this to this times the probability that I go from this to that. And if you add up all of those, you will get the probability that you go from this to that. Does this make sense? If no, you can actually say no. I'll try to explain it in some other way. Hello. Am I audible?
Yes, ma'am.
Oh, okay, yeah. Oh, good. So take your time to understand, I think. It's fine if I can give you guys like 1 or 2 minutes to try to explain this same concept to yourself. And if you can do that, then yes, you have understood this well enough, I would say. Let me just highlight this a bit because this is very, very, very important. Okay, so does anyone have any doubts so far? Or maybe what we can do is just to try to understand this even better, we will have a look at the examples. So not a big deal. But again, what I want you all to understand is the fact that if I want to figure out the probability of moving from I to J, it is indeed equal to summing up across all the possible values of K. I mean, first I just take any K that I always pass through, and the very fact that this K always exists is summarized by this diagram, right? So you don't have this question in your mind that, what if there is no K such, what if there is no K in between I and G? So from this diagram, it's pretty clear that you will always have a K in between I and J, which you pass through, right? And this K can vary. It can be anywhere here, depending on the sample path that you're looking at. So again, because you can figure out some time in between these guys, you take the state space that you can achieve at that particular time, and you demarcate these probabilities into two. So this one probability is now just the multiplication of this and that. And again, we are multiplying because it's and. This happens and then that happens. And if it were or, we would have added it. So now when I'm adding, so this represents and, right? Because we go from I to k and then we go from k to j. And what else can happen here? This k can differ. So I can either take this sample path or I can take this sample path. So when I'm talking about or, I'm summing them up. So I sum up all of these different probabilities for different sample paths. So when I'm summing up, I'm talking about different sample paths. But when I'm multiplying together, I'm talking about one, this, and then second transition from L to N. So I hope that's a bit clearer. And again, there is a set theory proof of, just trying to show you that this kind of stuff exists and everything. But again, just try to sink in the notations that we are using. So notation, I mean, it kind of looks tricky, but it's nothing. You write P, where P is, if I'm writing a small p, I mean, if I'm writing P, I, J, M, N, this represents a particular probability, right? And when I'm denoting a particular, let's say, so matrix notation, you have to get used to. And I think we'll solve a couple of sums and we'll see how that works. So this capital P represents this one matrix. And this P11 represents one particular element of that matrix. So I guess now we are ready to deep dive and study some kind of models. And I think maybe what we should start off now. So I've already explained to you guys, right? How does the time homogeneous and time inhomogeneous thing works? So here you know if you have 1, 1, 2, 3 equal to 3, 4 and so on, basically for n, n plus 1. And so if you want to generalize this same concept, you can actually rewrite it as P n comma n plus 1 from I to j is equal to Pij n plus k comma n plus k plus 1. So this would be a generalization of the time homogeneous case. Okay. And again, we know that if we are looking at time inhomogeneous, we have to figure out the other stuff. But again, when I'm writing Pij, it only denotes what's going to happen in one time step. So let us see what all do we know as of yet. So let us say if I have to figure out what happens in 0 time interval. So let us say I'm looking at only time homogeneous cases. Okay, forget about time inhomogeneity for now. I'm only taking into consideration time homogeneous cases. So let's say if I want to figure out my Pij in 0 time, what are the possibilities? Can anyone tell me? So what is the probability that I will move from state I to state j in 0 time period? So you can also take into consideration, let us consider our NCD model again. Okay. So, I mean, this Ij could be again anything. This Ij, so again, when I'm writing Ij, my I again, 1, 2, 3, okay, 1 denotes 0, 25 and 40% discount level. So again, remember the tricky part here is that there is no time elapsed. So what is the probability that you will move from state I to state J in 0 time period? Think about it. What do you guys think? So again, tell me one thing. Can you move from 0% discount level to 25% discount level in 0 time?
No, ma'am.
No, right? So for every time you will have your I, which is not equal to j, this probability is just going to be 0, right? And for every time your I is equal to j, this is going to be 1. Because, I mean, let's say if you are at 0% today, in 0 time, and basically, I mean, you will still be at 0%, right? So there's a chance of 1 of that happening if your I is j. So 0 to 0, yes, that will happen. But again, 0 to anything else, not possible. So it will always be 0. But again, this is for 0 time interval. And now let us say I have 1. So if I'm looking at today, and so I am at I today, and I want to be at j tomorrow. So this is just, in general, my Pij, right, by definition. So whenever I'm writing my this discount model, so I'm saying that, this is my, let's say my Pij. So this particular thing denotes my Pij, right? And this is a one-step transition matrix by definition. So what do we know? That whenever I'm looking at this one-step transition matrix, this is just going to be equivalent to whatever is given to me in the question, right? Does this make sense to you guys? What about Savri and Anvaya?
Can you please repeat this part of second
one? Okay, so what I'm trying to say here is that I move from state I to state j in one time period. So let us say today I am at I. So let us say today I am at 0% discount level. What is the chance that I will be at 25% discount level tomorrow? So we know that the way I have defined this transition matrix here, this was essentially just a one-step transition matrix. So whenever I say one step, I think there I was a bit unclear. So whenever I say one step, I mean one time period ahead. So one step means one time period ahead, and 2 steps means 2 time period ahead. So this is just one step transition matrix, right? So let's say if I'm at 0% today, what is the chance that I'm going to be at 0% tomorrow? 0.25. So again, these are denoted by P11 and P13. So these are my PIGs. So these will be given to me by definitions. So these will be given to you in question basically every time. You will know what is the chance of moving from this to that, from this to back to that. So this is exactly what will be happening in one time period pass, right? Does this make things better? Anvia?
Yes, ma'am.
Okay, good. What about you, Saudi?
It's clear, ma'am.
Clear. Okay, perfect. So now that we have yet cleared this, I think I should just, yeah, so I've written this, but again, you can also maybe to just, your books have something like this, but this is also fine. I mean, it says the same thing ideally. So yeah, I guess that is fine. Okay. So now we have done 0-step transition. We have done 1-step transition. Let me just write here. So this is like a 0-step transition. This is 1-step transition. Let us say now I have to figure out L-step transition. I shouldn't be using L. We can basically say anything. So let us say I'm looking at, B-step transition. So B can be basically any number which is greater than 1, okay? We know what's going to happen in 0. We know what's going to happen with 1. But now let us say we want to figure out what will happen. I mean, how do you figure out the chance that, let's say today you are at 0% and 2 time step ahead, you will still be at 0%. So again, if I were to, basically have a look at all of those chances of what all can happen. So I can go from this to this and then I can move back up here. That's one possibility, 1 time step, 2 time step, back to 0, or I can be 0, 0. So these are like 2 possibilities that I can actually have in this particular scenario. So if I go from 0 to 25, there's no way back to 0 in 2 time step. So you will either be 0, 25, 0 or 0, 0, 0. So these are 2. But again, this was a very easy example. So you could actually count the sample paths, right? You could count that my one sample path is 0, 0, 0, and my other is 0, 25, 0 back. So maybe you won't write the first zeros. I mean, if you don't want to write time 0. And yeah, so, but again, this is not something generalized. You can't possibly go about counting and adding up all of these every single time. So there is an easy way, and this is a very convenient and a powerful result, which says that if you want to look at this B-step transition, what you will only have to do is you take this. So basically, I'm looking at Pij and B time period, right? So what you will have to do is you take the matrix P. So this is my matrix P, and I raise it to power B. And that's it. And I check the ijth element of that particular matrix. So let us say, now if I have to figure out the probability that I will remain at 0% after 2 time steps, what will I have to do? I will have to just square this P. So are you guys familiar with matrix multiplication? Like how do I multiply a 3 by 3 matrix with another 3 by 3 matrix? Do you guys know that?
Yes, ma'am.
Everyone?
Yes, ma'am.
Okay. So I think I'll give you guys the exercise to do. So, but before that again, just to remind you guys that there is a rule of thumb, right? So let us say if I were to multiply this column with this sort of a matrix, I know that the number of columns in this guy should be equal to the number of rows so that I can do this by this multiplication, right? And if I'm trying to multiply this with this, I know that the number of rows in this matrix should be again equal to, sorry, the number of columns should be equal to the number of rows. So let's say if I'm trying to multiply m by n matrix times n by k, this is feasible. So this and this should agree, and this will render me a matrix which will be of dimensions m by k. So yeah, this is for matrix multiplication. Yeah. Okay, so now if you just raise your one-step transition matrix to B. So let us say we are looking at 2-step, or let us say even if we are looking at 10-step transition matrix, you can do easily. So you can easily raise this matrix to the power of 10 and then check its ijth element, right? And that will give you the B-step transition probability. And isn't that very convenient, I would say? Instead of trying to check all the possible sample paths, which you might as well can go beyond 100 or 150 and in complex situations. But again, this is a very convenient result, I would say. So what I would want you guys to do now is maybe a question. So let me open the book, I guess. What can be the page number? Okay. Can you guys see this question? I want you all to try and solve this question. And I'll take a 5 minutes break and I'll be back in 5 minutes. But by that time, try to see if you can solve this particular question. And transition graph is nothing but, the state space denoted in circles and then the arrows drawn around those for each state space. So I think just give me 5 minutes. I'll be back in 5 minutes. And by that time, I guess you guys can see if you can solve this question or not. And I'll discuss once I'm back. Is that okay?
Yes, ma'am.
didn't get recorded. Hello. Yeah, I'm audible, right?
Yes, ma'am.
Just give me 2 minutes, guys. Do you all remember what did I explain after the break? I think I explained. Oh, I've explained quite a lot, I think. Well, let's see. I have no idea, I guess. Let me just check one. Let's just continue. So what I was talking about is, let us say we are looking at 0-step probability, right? And what I'm talking about is that I am at time step 0 today. So what's going to happen next is that I will be at 0 here, and I'll have a 0 here as well, right? Because I can only be in this state space where I am currently at one moment in time. So I'll have a 0 here and a 0 there. So this is how you start off with a vector. So this will be your time 0 step. And now if once you have this vector, you will check with the transition probability. So you will multiply this. So let me just write it as a vector. You will multiply this row vector with a matrix, which will be your transition probability. And this will basically take you from 0 step to 1st step, and then again and then again. So here in what you're doing is, instead of multiplying the whole matrix thrice, you can just start off with 1, 0, 0. So this will be a time 0. And again, you'll be multiplying it 3 times. So let's say time 1, time 2, and then time 3. So you multiply it twice again. But the calculation will be much more simplified because here you're starting with 1, 0, 0. So if you basically, you'll only have to always work with row vectors. So if you multiply this, which is, let's say, 1 by 3, and this is a 3 by 3, you'll get a 1 by 3, and so on and so forth. So at the end, you will have a 1 by 3 vector. So once you have multiplied this and this, and I know that this answer should be 9 upon 16, right? Because that is what I'm looking at. So from 0 to 2 in 3 time steps. So I've multiplied this transition matrix thrice, and you will end up with 9 upon 16 here. Is this clear to everyone? Does this make sense? Do you guys want to try this multiplication?
Ma'am, can you explain it once again?
Okay, so basically what I said is, as of now, what we did was, we cubed this transition matrix, right? So what I'm doing now is, instead of starting at time 1, I'm starting from time 0. So I'm taking my today's situation into account as well. But what is my today's situation? Today I am at 0 state, right? Today I'm at 0 state space. So again, if I'm at 0 state space today, I can write a 1 here and I will have 0 elsewhere, because this row and column both represent today's scenario. So this is a zero step transition. So we have already looked at that, if let's say I have a 0 step transition, then only if my I is equal to j, it will have a probability of 1. Otherwise it's 0, because I can't be at state 0 and state 2 in the same time. I can only be at one state, which is the current state, in time 0 as well. I mean, time 0 is just like, basically it's just the state where you are at. So this is a vector that you get. So again, I mean, you did not even think that much about it, but that was just to make you guys understand why do we have 1 0 0. But the very simple thing you can always do is put 1 in the state space wherever you're starting from. So let us say if we were looking at P1 2, then your this vector would be something 0, 1, 0, because you're starting at 1, right? So your 1 would be here. And let's say if you were starting at 2, then this would be 0, 0, and 1 here. So this denotes your starting point, your initial point, the place where you're starting from. And then what you do is for the first step. So this is my first step, right? So this was time 0, this will be time 1. So again, how do I know where will I move in the next time period? That is denoted by this transition matrix, right? So I will multiply this row vector with this thing here. So I will be multiplying 1 0 0 with these transition matrix here. And if I multiply it once, I will get my time 1, right? I mean, what's going to happen in time 1? And if you do that, you will get the same answer as 1 by 4. So let us say if I multiply this with this guy, what will I get? I will get 1 by 4, 3 by 4, and 0. So what in essence you're doing is you cut these rows out. And because you don't need this, right? What you need is कि 0 से तुम 2 वाले state में कब जाओगे? So if you're starting at 0 state, always only the first row is what you have to concern yourselves with. So you're only going to get, corresponding numbers for that one particular row. So once you multiply this with that, you get something like this, which is again one step transition matrix, which is the same thing as this, right? Done. And now again, if you want to have a look at what happens in another time period, you will multiply this vector with again the transition matrix. And once you do that, you will again get one particular vector. So let me show you again. What's going to happen is, so see, to start off with, you started off with something like that, and then you multiply it with P, and then you will obtain, for 1, it would just be, 1 by 4, 3 by 4, and 0. And then for 2, it will give you something like this. And then for 3, it will give you something like this. And then again, we know that we were looking at a transition from state 0 to 2. So this is a vector which only represents transition from state 0, nothing else. So to go to 2, we know we have to look at these 1, 3. So it is 9 upon 16. So that is all that matters. And you get that easily. So you don't have to, figure out those. So you save your calculation of this step and this step. So 6 there and 6 here. And this is kind of a shortcut way to, work with the transition probabilities and figure out stuff. Does this make some sense?
Yes, ma'am.
Good. What about the rest of you guys?
Yes, ma'am.
Yes, ma'am.
Okay, so now I think what you guys can do is, I think you guys should try. So again, you take the same example and you try to calculate the probability that with a discount level of 25%, you end up 4 years later at the same level. So tell me, what will you start off with? What will be my starting vector? Anyone? So I'm starting at a discount of 25%.
Zero, 1, 0.
Exactly right. 0, 1, 0, because 25% denotes this particular state. Okay. So now what you have to do is you have to look at 4 years later. So again, sometimes people get confused with what's going to happen. Like, how many times do I have to multiply this with P? So easiest thing to do is draw these curves. Okay. So this is at 0, then time 1. 1 year later, 2 year later, 3 year later, and 4 year later, right? So this is what will be your answer. So you have to multiply it once, then again, and then again. So can you guys do this? I think you guys should just try this to check with, there is a possibility that you might do some mechanical errors or something like that, but I can just try to do that. Until then, I think I will just explain what the other guys who are not present in the live lecture missed. Oh, I paused the recording. Is that okay for you guys? So just try
Yes,
to do
ma'am.
this and I'll go through the part again. Basically, I'll try to explain myself. Don't answer any questions from now on. Okay, so for the missed recording part, I'm just trying to go through this again. So when I told you guys to solve this particular question, to figure out the values of P and Q, what you will just have to do is, we know that all of these values in a particular row should add up to 1. So again, we know that P minus 0.05 plus 0.07 plus 0.22 should be equal to 1. And if you solve that, you will get P equals to 0.6. And using that, you can get this particular Q's value, which is just going to be 0.4. And the next step asks us to figure out the transition probabilities. So again, when I'm writing this, you see they have written small pj here, right? So because they mean the transition probabilities, which are 9 of these for each I and j, going from 1 to 3. So again, they could have also written calculate the transition matrix, capital P and 3 up in subscript. So that would again still mean the same. So what you will be doing is you will just have to multiply this P thrice, which is the transition matrix, and what you will get is something like this. And again, this as a whole is a transition matrix, and these particular probabilities are transition probabilities, and these elements are denoted by small pij. And we have this 3 in the subscript here because we're looking at 3 times ahead. So I guess that's clear. And again, whenever you're looking at P's cube, I mean, we can use the association property, and it doesn't matter if you multiply P squared with P. So it's just basically saying here that, let's say, if you have to figure out P4, you shouldn't do, P times P times P times P. So you shouldn't do it like this. No. The easiest way to do is this and this. So what you can do is P squared. So you just figure out 1 P square and then you multiply it together. So you take a power of it, P square times P square. That will give you P raised to 4. So you don't have to do these many multiplications. We'll just have to do 2 of them. So I guess that's clear. And then you figure out this transition graph. So again, remember, whenever we are writing transition graph, by default, it means one-step transition graph. So this is just one step ahead. So you don't go and plot this. You plot what you started off with here. So 0, 1, 2. And these arrows, so 0 to 1 will be 0.6. 0 to 0 is 0.6, 0 to 1 will be 0.4, and so on and so forth. So remember, we only plot arrows for the transition probabilities where we have a value greater than 0. So this guy has 0, so you don't have to denote an arrow for that. So that was it. And then we went on to discuss the other sum. Yeah. So then I was discussing this model, wherein what I said was, I mean, this is kind of the same model, except that here I have 50% instead of the 40% that we were discussing up until now. And this is the same transition matrix that you have. And again, what they are asking us to calculate is the probability that in 3 years, let's say, you go from state 0 to state 2, which is that you go from 0% discount level to 50% discount level in 3 years. Again, if my time period denotes 1 year. So to figure that out, you can actually take the cube root of this P. You can calculate its square and then multiply it again with P. And then you can check this particular value, right? Because from 0 to 50% is from state 0 to 2. And this represents state 0 and this represents state 2. and this represents state 0 as well. So 0 to 2, which is this particular thing right here. So this is the P, so I don't care about this, but this will be the location in P cube, and the answer is actually 9/16. And that was it. And then we went on to actually do it in another way, which is an alternative approach, where you can actually see what all steps are possible, and you multiply it with, and you multiply all the probabilities. So again, this is similar to the Chapman Kolmogorov equation that we saw previously. So this is the probability that you will go from 0 to 0 is 1/4, 0 to 1, 3/4, 1 to 2, 3/4. So you add up both of these, and these are like the two different sample paths that you can have. So I'm multiplying here basically 0 to 0 and 0 to 1 and 0 and 1 to 2. And either this can happen or this can happen, right? So I'm going to add up these and I get my answer as 9/16. Or else what I can do is this thing, and I guess what we can do is, otherwise we can start at time step 1, and then, otherwise we can start at time step 0. So this will be a vector that represents where you currently are, which state you currently are positioned into, and then you will just multiply it with P and you will get the required probability. Yeah. Did you guys try the question? And yeah, I was done with recapturing of what you guys must have lost. So you should get answers, which is something like this here. Okay, so you don't have to basically see all of these parts. Yeah, we'll be following this method right here. So again, you don't even have to figure out this and this part. You can choose to skip them because this is what is the required probability. So like you have this as the answer, that's fine. Any doubts with this? You guys hear me back, okay? I'm done with recalling what they lost. Now you guys have to respond to me. Am I audible?
Yes, ma'am.
Okay. Did you guys get the same answer?
Yes, ma'am.
Yes, ma'am.
Okay, if not, there must be just some mechanical error, I would say, and you should just try to go. What just happened? Like that. Yeah, so you should basically just try to, check what is. Okay, so now let us see what happens in the next scenario. Yeah. So what we saw as of now was again, just a time homogeneous model, right? We said that my transition matrix P is constant every single time, right? So my one-step transition probability, whether I go from 1 to 2 or 2 to 3, is going to be the same. But again, this need not always be the case, as we have discussed earlier. So when that is not the case, we are looking at a time inhomogeneous model. So it's very evident, it's clear that, I'm not going to write my transition matrix in the same way that I just wrote now. So I'll have some subscript which will denote what time period this transition matrix refers to. So can you guys think of a particular scenario in real life situation of how would you convert this no claims discount model, which is time homogeneous now, to a time inhomogeneous case? So basically, what condition would you see? What change do you think can happen in this particular case? What is it that will make a claim depend on the time? So again, I think the the easiest and the intuitive way to consider this, let us define a time period in terms of months rather than years. So my one time step is, let's say, one particular month. So I go from January to February, then February to March, and so on and so forth. So we know that in times of monsoon, there is a higher chance of an accident, right? Because the road being slippery or something else. I mean, these are just cooked up reasons, I would say, but some of the real life examples would actually suit the purposes of modeling using a time inhomogeneous model. So what you will do is, instead of, I think, let me just save some time from writing this stuff again. And what I can do is just share the book. How will I make this go away? Oh yeah, that is. Yeah. So now if I'm looking at time inhomogeneous case, what I write here is, instead of just writing P0 to 1, I will have to write in bracket T to denote that this is the P01 if you're starting at time T, right? And this is P00 if you're starting at time T. Because this probability, the probability that you will stay at 0% discount level will change if you're looking at today or if you're looking at tomorrow. So let us say today the probability that you will stay at 0% the next year is 25%. It will change, or it can change from, let's say if you're looking at tomorrow to day after tomorrow. So it might not be 0.25, 0.25 the next time. So here you will write 1. So P001. And that is why you just have this little t's in brackets everywhere and here as well in the transition matrix. So again, now the transition matrix as a whole will also be denoted as PT. So including all the transition probabilities which you get directly from here. So I guess that's pretty much clear. And again, you know, this is never going to happen. So you can write 0. And that's just about it. So this is what is going to, this is what a time inhomogeneous model for this no claims discount would look like. Does this make sense to you guys? Any doubts?
And can you please tell once again, why do we write T in the bracket?
Okay, so we write T in the bracket because let us say, Anvaya, the chance that, so let me say that, you know, we are looking at different time periods. Let me try to write. Okay, so I'm looking at time period 1, time period 2, and time period 3. So first, I'm concerned with the probability that I go from, so this is 1, 2, 3, let's say this is my time, and let me denote my I, J, K as my states, okay? So the probability that I go from I to J in one time step, sorry, let me just take, so let me just take this example, okay? So we have state 0, state 1, and state 2, and we have 10 different times. So let me just denote time by T, T plus 1, and T plus 2. So this is my time, and I have states. This is 0, this is 1, and this is 2. This is clear, right? And now what I want to figure out is the probability that I go from state 0 to state 1 when I start at time T and I end up at time T plus 1. And the same probability, but at different times, T plus 1, T plus 2. So this says that I am at state 0 at in time T, and I move to state 1 in time T plus 1. And this says that I am at state 0 in time T plus 1, and I move to state 1 in time T plus 2. So if you see the lag here, I'm moving one step forward here, and so am I moving here as well. One step forward, which is the same. So if this were a time homogeneous case, this would be equal. But now this is not time homogeneous. So these are not equal. So basically I'm saying that the chance that you go from 0 to 1 in one time state depends on the time that you start off at, and not only on the increment in the time. Does this make it a bit clearer?
Yes, ma'am.
Okay, good. What about the rest of you guys?
Yes, ma'am, it's clear.
Yes, ma'am.
Good. So I guess that is it about, this. But again, now let us have a look. So there is actually an example as well in your book itself. Why is this not working? Yeah. Yeah. So now let us try to solve this particular question. This is about a time inhomogeneous case, I guess. I'm not sure. Let us see what this question is. So, who will want to read this question, I guess? I mean, just read it in terms of words, I would say. Just try to explain what this question tells you and what does it asks you to calculate. Anyone of you? Anyone? Anyone would like to volunteer? No one? Savri? Can you read the question?
Yes.
I mean, don't
Yes,
read
ma'am.
it word by word, but just try to explain what do you understand of the question.
Ma'am, as far as I've understood, we have given that xn is xn is dependent on xn minus 1 and yn, and yn can take the value 0 and 1, and then according to that we have to draw the transition diagram.
For xn, right?
Sorry.
Yeah, so we have to draw the transition diagram for xn.
Yes.
Yeah.
Correct.
So what do you guys think I should start off with? So do we know what is the value of x0? It is 0, right? It's given to us in the question itself. Good. So now we'll see what are all the possible values that x1 can take. So what do you think are the possible values that x1 can take?
It will be 1 by 4, right?
1 by 4.
Oh, no, sorry, no.
So, okay, so this is the probability that your y1 will be 1. So remember, whatever xn you have, it is made up of the previous value of x plus this some noise, which is yn, and we know that it only takes the value 0 and 1. And they've given the probability that y1 will be 1 is 1 by 4. And for the other n's, where let's say n starts from 1, so from y2, y3 onwards, the probability that it will be 1 is summarized by this. So by looking at this equation, what do you guys think? Is my y Markov? Like, does my y follow Markov property? What do you guys think? By looking at that equation? Do you guys think my yn has a Markov property? Okay, so good question to start off with. I guess can be, let's say, if let's say my yn has a Markov property, then what should my yn plus 1 depend on?
Yn, right?
Yeah, so my yn plus 1 should ideally depend only on yn, right? And is that true in this case?
No.
And why do you think so?
It's also depending on the value, previous value of x, right?
Yeah, right. So again, because my yn plus 1, I can clearly see that it depends on xn. And what is my xn? My xn depends on xn minus 1 and yn. And my xn minus 1 depends on, like my xn value depends on yn minus 1, yn minus 2, and so on till y1, right? So this is not ideally Markov. It doesn't satisfy all the properties of Markov. But we'll see whether my xn follows Markov property or not. But again, we aren't asked to do that. What we have to figure out is the transition probabilities for xn. So I know what is my x0. It is just 0. But now if I have to figure out my x1, what are the values that my x1 can take? Anyone? Can you tell me what are the possible values for x1?
It will be 0.
Exactly, right? It can, so I know that my x1 using this equation can be written as x0 plus yn. And I know that my x0 is 0 always. So my x1 is just equal to yn, which can either be 0 or 1. And so will the values that my x1 will take. So my x1 can either be 0 or 1. But now I have to check what is the probability that my x1 is 0 and what is the probability that my x1 is 1. And how do you guys think I should figure that out? So the probability that my x1 takes a value 0, given that my x0 is 0, and so let's just try to figure this, right? Because 1 minus this is going to be the other. Yeah, so how do you guys think I should go about solving this? Because remember, the transition diagram not only includes the possible values of x1, but it also includes the probabilities, right? So if you just write the state space, that's not the complete diagram. You have to write the probabilities as well. So how will you figure out this probability? Anyone?
Ma'am, is it like for calculating probability x1 is equal to 0, we can substitute n is equal to 1 in that equation, xn is equal to n is equal to x0 plus y1, and then probability of y1 is 1 by 4.
Wait, what did you say? What should I substitute 0 in?
In the equation xn is equal to xn minus 1 plus yn, we will substitute n is equal to 1 because we have to calculate probability of x1 is equal to 0, right?
Yeah, right. So instead of x1, you say I should just write it as xn minus 1 plus yn equal to 0, such that my x0 is 0, right?
Yes, ma'am.
And this xn minus 1 I know is just 0. I mean, I should ideally just write x0 here, right? So this is just 0. So what it boils down to is the probability that my yn is 0. And what is the answer to this? Sorry, I shouldn't even write yn, right? It should
Y1.
be,
Yeah.
yeah, it should just be y1. So yeah. So the probability that I will observe my y1 as 0 will be 1 minus of this, right? Do you guys agree? So because I know that my y can only take two values, 0 and 1, and if the probability that my y1 takes a value of 1 is 1 by 4, then I know that these events are mutually exhaustive and exclusive. So the probability that probability that y1 will be 0 is equal to 1 minus the probability that my y1 will be 1. So this is just going to be 1 minus 1 upon 4, which gives you the answer 3 by 4. So if you start at 0 and you end up with 0, that's going to happen with a chance of 3 by 4. And as we know that this and this is the only possibility. So this will just be 1 minus 3 by 4, which is what? 1 by 4. Is this clear to everyone? Savri and Via?
Yes, ma'am.
Yes, ma'am.
Okay, good. So now that we are at x1, so we know the values that x1 can take 0, 1 with these probabilities. Good. So now we have to figure out what's going to happen with x2, right? So we did x1, but now we also have to look at what can happen next. So we have the possible values of x1 as 0 and 1. So what do you guys think will be the possible values for x2? So remember my xn is xn minus 1 plus yn, where my yn can take values 0 and 1. So if my x1 is 0, yes.
Sorry, it will be 1 or 2, right?
It can be the 1 or 2. Okay. Does everyone agree with what she has just said?
It can be 0 too, right?
Exactly right. It can also be 0. So the best way to do this is, just take one value of x1, which is 0. So you try to figure out all the possible values for x2 when you have x1 as 0. So I know my yn can be 0 and 1. So let us say if it's 0, it's going to be 0. And if it's 1, it's going to be 1, right? And then you take another value of x1, which is 1. And now you check for all the values of yn. And if this is 0, it's going to give me 1. And if this is 1, it's going to give me a value of 2. So my plausible answers can be these. So 0, 1, 1, 2. So either this can be the 0, 1, or 2. Right? So again, from 0, I can only go to 0 and 1. And from 1, I can go to either 1 or 2. But now I have to figure out what is the chance of these happening. So how do I do that? So to do this thing, basically, what you will have to use is this particular equation right here. So again, remember this probability that y1 will take the value of 1 is only true for n equals to 1, right? It is only true when your t is 1. But for all these values where you get a subscript here which is greater than 1, this equation is what you have to refer to. So again, remember, now when I'm trying to have a look at what is the probability that if I start from 0, I will also end up at 0. When does this happen? This happens when my y also takes a value of 0, right? But I think the easier thing to work with is when your y takes a value 1, because this is what is clearly given to you in terms of this. You could also work with 0 but you will just have to take 1 minus of this thing. So it will still give you the same answer. But let me just try to explain this now. So yeah, if you are trying to figure out the chance that you will go from 0 to 1, this is the equation that you will have, right? And this is just being equivalent to the fact that you observe a y2 of 1, given that you are starting at 0. So again, so what you did was you just substituted xn here. So you see the difference. This is x1 and this is y2. So this is yn plus 1, where your n is just 1. So let me maybe write it. If you compare this, so again, whatever value your xn takes, it doesn't really matter. So what you're going to do is you'll have 1 upon 6, 1 plus the value of xn upon 1, right? So was this upon 1? I mean, to write upon 1 doesn't make much sense. Oh, this is upon n, right? So yeah, here your n is 1 and that is why you're dividing it again by 1. So I guess, yeah, that's it. Does this make sense? So this is basically how you will figure out this particular probability. And now you can put arrows in middle too. That's just fine. But now I know that from 0, I can only go either to 0 or 1. And I know that basically it's the same fact, So this means that my rows should add up to 1. So I know that I can never go from 0 to 2. So let us say this is my 0 here and I have 0, 1, 2 here. So I know I can never go from 0 to 2. So this will be 0. And from 0 to 1, the probability is 1 by 6. So you know that the probability here should ideally be 5 by 6, which is just 1 minus 1 by 6. Does this make sense? So again, what we did was we used the equation that was given to us in the question itself, which was something like this. So even though it didn't specifically say that this is a conditional probability, we know that, my yn plus 1 doesn't anyways depend on what my value of xn is, right? So this is just going to be equivalent to this probability. But here you just know what the value of your xn is going to be. So you substitute that value of xn here. And because we have yn plus 1 here in the subscript, and we were looking at y2, if you compare this 2 and n plus 1, you get the value of n as 1. And that is why everywhere you have, and this is x1, right? So it kind of makes sense. And you know the value of x1, which you're actually looking for here, which is 0. So for 0 x1 value, you will get 1 by 6 as the answer, which is direct. And now again, to have a look at this other scenario, what you will have to do is, you will have to start off with 1. So instead of 0, now you have a 1 here, right? And again, your n will stay the same because again, you're still looking at y2 and x1. So yeah, here they have written it deliberately. So I guess this is it. So this is how you will get the answer. Let's say 1 by 3 here. So you will get your 2-step transition here. So 1 by 3, 2 by 3, basically 1 minus 1 by 3. And then you're again going to use the same thing to branch it out and branch it out. And you will end up with this. And this is your transition diagram, the complete transition diagram. So any doubts so far with this? Any doubts? Anyone? So I would suggest that, you guys should try the rest of the branching out that I didn't carry out the lecture now by yourself and without looking at the book to see whether you understand how to do it. But again, it's just, the same thing. You will just have to substitute in for the formula and you'll basically get to your probabilities. So I guess that's all from my side for today, and we'll continue with next series of models in the next lecture, which is tomorrow. Any doubts? Anyone?
It's clear, ma'am. Thank you.
Okay, thank you very much.
Thank you, ma'am.
Thank you, ma'am.
Okay, I'll see you guys tomorrow then. Try to solve the rest of the branches, I would say. That's it.